Okay, this came up on a higher tier GCSE Physics paper a few years ago. So we'll start with question 8. Figure 11 shows a toy car in different positions on a racing track. So we see we have A, it's going down the track, and we have B, C, and D. 8.1, the toy car and racing track can be modeled as a closed system. Why can the car and the racing track be considered a closed system? Well, let's recap what we mean by a closed system. In a closed system, we mean that energy and matter cannot leave the system or enter the system. Okay, so what we start with is what we end up with. The energy we start with, the energy we end up with. Think of a thermos flask. You want it to have hot coffee in it. You put your hot coffee in the morning, and you put the top on. That is going to stay hot for the majority of the day. No thermal energy can escape. Well, what's a flask got to do with this racing track? If you think about it, as the car travels down this track, the wheels are in contact with the track. So that's going to create friction. Friction creates thermal energy that could slow down the track, slow down the car. Similarly, as the car goes down the track, the car is going to be in contact with air particles, and they are going to cause air resistance. Now, normally we would have to take into account those, but when we are talking about a closed system, we ignore air resistance in this case and the friction from the track. Okay, so the energy we have at the top of the ramp must equal the energy right at the bottom. In other words, you see we have the bottom one here, the total energy of the racing track, and the car is constant. Okay, there's no change in energy from the top of the track to the energy that the car has at the bottom. And that's the answer to that one. And that's really, really going to be important when we look at the next part of this question, that closed system. So let's have a look. 8.2. The car is released from rest position A and accelerates down due to gravity down the track to position B. So we have it at A. Accelerating means it's changing speed with time. The speed is increasing. It's accelerating all the way down to B. Now we have the mass of the toy car given as 0.040 kilograms. The vertical height between position A and B given as 0.9 centimeters. Let's just pop that here so we can see. That's what we mean here. This vertical height is 0.9 centimeters. Now, and the gravitational field strength is given as 9.8 newtons per kilogram. Straight away, though, I can see here, and this is what we need to remember in physics, those unit conversions, when we are looking at height or lengths, we want those in meters. There's 100 centimeters in 1 meter, so we're going to divide that through by 100, and we'll get 0.9 meters here. Okay, so 0.9 is that distance. That's really important. So let's get our units right. We have kilograms, that's correct. Newtons per kilogram for our gravitational field strength. Now, you may know that that is also an acceleration. It simplifies to meters per second squared, but we're going to keep it as newtons per kilogram. Okay, so calculate the maximum possible speed of the toy car when it reaches position B, so when it's right down here. Remember what I said about that closed system. We're not including air resistance or friction. So the energy, the total energy it had up here, we're going to call that gravitational potential energy, is converted completely into, and in this case, the car's moving very quickly. Here at B, we're going to call that kinetic energy. So all of the gravitational potential energy here is converted into kinetic energy here. Okay, so let's write down what we have. Now, I always like to write everything that I have down. It makes it nice and easy. So we have mass is 0.04 kilograms. We have the height, so that's h, is 0.9 meters. And we have gravity on Earth as 9.8 newtons per meter kilograms. Okay, we're going to look at our equation sheet. We're going to look at the quantities that we need here. And what equation are we going to use? Which energy equation are we going to need? Now, it's asking for the maximal possible speed, but This is a 5-mark question. When we see 5-mark questions in GCSE Physics, equation questions, we are going to need to use 2 equations, or sometimes we need to use 1 equation, but we need to use it several times. In this case, we're going to need to use 2 energy equations. So let's see what we've got. Well, I look at my equation sheet and I can see that I have gravitational potential energy, that's E, small p, is equal to mg gravity and h height. We're going to pop in our units here now, what we have, 0.4 times 9.8 times by the height is 0.9. I'm going to enter that into my calculator. Let me see what I have here. Right, yeah, and I have got 0.3528, realizing that it's an energy, that is joules. Okay, now we've got the energy, we've got the gravitational potential energy now at the top. Now, remembering that that is all going to be converted into kinetic energy. So let's just do our mark scheme here. We're going to get 1 mark for using the equation, the correct equation, and we're going to get another mark for getting the correct answer. You're not going to get a mark for writing out the equation, mgh, and you're not going to get a mark in the exam for writing out the units on the side, although it's really good practice to do that. But we'll get a mark for using the equation and a mark for getting the answer. Okay, so we need to work out the possible speed. Right, I'm going to use a black pen for this next one. So what equation do we have? What energy equation can we have that has speed in it? Well, I look at my sheet and I see that it is the kinetic energy equation, 0.5 mass times velocity squared. Velocity is our speed. That's what we're going to need here. We're going to need the speed. Okay. Now we're going to equate it. Remember that all of that potential energy has been turned into kinetic energy. So let's write that out. We have 0.3528 joules. I'm not going to write the units yet. Is equal to 0.5 times, and we've got our mass, which was 0.04. And that is going to give me, when I put that into my calculator, 3528 is going to give me 0. What do I get? 0.2 v squared. So we have 0.3528 joules is equal to 0.02 v squared. We need to isolate v. What we're going to do is we're going to rearrange the equation. So I'm going to divide through by 0.02 to get v squared on its own. So 0.3528 divided by 0.02 is going to give me v squared. But is that what we need? Well, we can put that into our calculator and get the v squared, but we need v on its own. So we're going to square root both sides. Let's do that big here. And we're going to enter that 0.3528. And we're going to divide all that through by 0.02. That's all square rooted, and that's going to give us v, our speed. And when we enter that into our calculator, we're going to get 4.2, and we're already given the units meters per second. Okay, and that's the answer to that. Hopefully that helps. But let's just look at the mark scheme. We're going to get a mark for using the equation here. So that's another mark here. Using this equation, we're going to get another mark for that rearrangement, and we're going to get a mark for the answer. That's our 5 marks there. Okay, let's move on to the next one.